for this problem, we need to prove that the Laplace transform of t raised to n times u of t is equals to n factorial over s raised to n plus 1 factorial. Let's start. The integral from 0 to infinity e raised to n times e raised to negative s t dt. We can recall that u of t is already equals to 1, so I didn't include this into the equation. And by using integration by parts, our u is equals to t over n, our du is n t raised to n minus 1. Our dv is e raised to negative st dt, and our v is equals to 1 over s negative times e raised to negative st. So we have already come up with the u, du, dv, and v. So substitute it. Our u is t raised to n times our v is negative 1 over s times e raised to negative st with 0 to a as a positive, as a very large number, minus the integrals of negative 1 over s times e raised to negative st, and our dt and our du, by the way, is times n t raised to n minus 1 dt. I forgot the dt. There. Don't forget that the du is this one and not this one, because this is dv. So as you can see, just by looking at this part of the equation, we can already say mentally that a, when you substitute a into this equation, that e raised to a as a very large number, it is 0, and with 0 substitute into this, multiply into this, it is already 0. So our first part is already 0. So that leaves us with this. So when we simplify this, I will simply move out the integral sign, our constant, and our constant will be n raised to s. It is positive n over s because negative times negative is positive, and n is multiplied over 1 over s times integral of e raised to negative st t raised to n minus 1 dt. And when you look at this, we can say that this integral is saying that the Laplace of t raised to n minus 1. So you don't need to integrate it, but instead just equate it by using n over s times the Laplace of t raised to n minus 1 without dt. So you have come up with a recursion equation that you need the multiple numbers of n in order to solve the final equation. And we will substitute n with 3 numbers, so 1, 2, and 3. So we'll first start with n is equals to 1. Now substitute 1 into these equations. 1 over s times the Laplace of t raised to 1 minus 1. So 1 minus 1 is 0 and t raised to 0 is 1. So as you can recall, the Laplace of 1 is equals to 1 over s. So 1 over s times the Laplace of 1 is 1 over s. So when n is equals to 1, our value is 1 over s squared. Next is n is equals to 2. Over s times the Laplace of t, 2 minus 1, and 2 minus 1 is 1, and the Laplace of t, as you also recall on a previous example, is the Laplace of t is 1 over s squared. 1 over s squared. So, when n is equals to 2, our solution is 2 over s cubed. Now, for n is equals to 3. 3 over s times the Laplace of t, 3 minus 1 is 2, and if t raised to 1 is 1 over s squared, then t squared and its Laplace is 2 raised to s cubed. So, multiplied, when n is equals to 3, we have 6 over s fourth, or 3 factorial s4. So, when you look at the solutions of n that we have encountered, we came up with an equation of this as 1 factorial s squared, and this is 2 factorial over s cubed. So, n factorial over s n plus 1. And that is how we prove that the Laplace of t raised to n times u of t is equals to n factorial over s raised to n plus 1.